Okay. Wait. Okay. I first want to thank the organizers, Alfredo, Marcel, Tino, and Marcos, for the invitation and for this wonderful conference, for the wonderful dinner, and not for the schedule because I took only one caipirinha. Okay, and thank you that are here after this night. Okay, so I'm going to talk about the semi-classical approach to work distribution. I am Diego Wisniacki. I am from the University of Buenos Aires. Sorry. Okay. As all of you know, there is an incredible development in many experimental techniques like atoms in optical lattices, ion traps, or in Josephson qubits. Okay, in this type of systems, there is a mixture of two different theories. There are, of course, quantum systems, and there are many-body systems in which thermodynamics are important. These developments develop a new area, a new subject, that the name is quantum thermodynamics. So essentially, quantum thermodynamics try to solve, for example, how thermodynamics emerge from quantum mechanics. This is an old question. The quantum effects in thermodynamics as many-body localization or coherence. What are the effects in many-body system? Okay. There are other important point in quantum thermodynamics is to apply many new techniques that come from quantum information to thermodynamics. One of these is, for example, research theory that was applied for entanglement, that now was applied recently to coherence, and people are trying to apply to non-Markovian, okay? And people use in quantum thermodynamics. It differs from quantum statistical mechanics because the emphasis is in the dynamical process out of equilibrium. Okay, and also people use in quantum thermodynamics try to use not many body, and sometimes like take one atom and use as a to make heat and work. Okay, so these are the several ideas that people are trying to solve in quantum thermodynamics, and of course if you take a basic book of thermodynamics. Thermodynamics, the definition of thermodynamics is the connection or the relation between work and heat. Today, I'm gonna talk about work, okay? And work in quantum thermodynamics in quantum mechanics is a different, as Fabrizio told you, it's difficult, okay? So one way that people use to define the work is the two-measurement process that Fabrizio described. I'm going to show you, I'm going to repeat essentially what Fabrizio said in a different way. Okay, what is the two-measurement process? Essentially, the idea is that you have a quantum system. This is a dead cat, okay, or alive. And you put the system in contact with a thermal reservoir, because you need that the system is in a thermal state. Then you, cut the contact with the thermal reservoir, and of course the system has a Hamiltonian, okay, and the Hamiltonian has some parameter, okay, and the idea is at t equal to 0, you measure the energy of the system, okay. It is the first measurement of the system. Then you make the process, the thermodynamic process. You change the piston, you change the magnetic field or whatever, okay? And then at some time, you measure again the energy, okay? And if I ask, what is the work done on the system? Of course, all of you will say this is the final energy minus the initial energy, okay? These are the two values that in this realization we measure, okay? But of course, as Fabrizio said, it is not possible to define an operator because the number of results of the work are much greater than the number of elements in the Hilbert space, okay? So, work is not represented by an Hermitian operator, as Fabrizio said. It's a random variable, okay? And, well, this is the definition. This is a copy of a paper. I don't remember which paper, okay? The definition is rather subtle in quantum mechanics, okay? So, essentially, this is the probability of work that comes from the two measurement process. This has two probabilities. Okay, this is an stochastic quantity. And the first probability, this PG, is related with the initial state, with the thermal initial state. I am starting with a thermal state, okay? And the other probability comes from the evolution, from the process, okay? It's the conditional probability to obtain the final energy at the final measurement, given that the initial measurement was this one, okay? Okay, so it's very easy to show that with this probability of work, you can easily fulfill the Harsinski equality. Okay, the Harsinski equality, I remember like 10 years ago, I took a course of new advances in statistical mechanics, and the teacher said the Harsinski equality identity is the most important result of statistical mechanics in the last 50 years. Okay? Essentially, the Harsinski equality allows one to determine the equilibrium free energy, this is in the left side of the identity, through measurements of non-equilibrium work. Okay? Here is non-equilibrium, and here is equilibrium. Okay? So, after the initial paper of Harsinski, this was the first paper. I remember I read at that time and I didn't understand anything. And after this paper, people try to test if this equality works. And in fact, people test this equality in several experimental of different experiments. This is the first one. This is an experiment for the stretching of a RNA molecule. This is a biological experiment from Carlos Bustamante. Then this is an example of a torsion pendulum. They test the Harsinski equality. This is an electronic system. This is other electronic system. This is an NMR experiment when they reconstruct the probability of work. They don't do the two measurement process. The first quantum test of the Harsinski equality is this one from the people from China. They did for one ion trap, okay? And they apply this two measurement process. And this is another one. This is a recent paper in an atom chip. I think they put a Beck inside the atom chip, and they test the Harsinski equality. So essentially, this is a recent paper of the Harsinski. It's talk about the probability of work. And they said, while this two-point measurement definition of quantum work can be justified heuristically by appeal to the first law of thermodynamics, its relation to the classical definition of work has not been carefully examined. Okay? The idea of this paper is we have the classical probability of work. Okay, it's very simple. We have the quantum. And he say, okay, let's see if the two measurement process, it's okay, this definition is okay, making a semiclassical theory. And this semiclassical theory is the bridge between this classical and quantum works. Okay? And in fact, they did that for a very simple system. They make a semiclassical theory for this one-dimensional system. It's a quartic oscillator, and the process is to change linearly the parameter lambda, okay, with time. And they make a semiclassical theory, and they show that this works nice, okay? And at the end of the paper, say, okay, we solve a very simple system. Now, the good point is to do the same for a complex system, a chaotic system. And they say that probably this is very difficult because in a chaotic system, the number of trajectories grow exponential and all that. Okay. This is exactly, so my point here is we want to see the corresponds, the quantum to classical correspond of the probability of work in a chaotic system. This is the goal. I want to make a semi-classical theory of PW, okay, in a chaotic system. This is what I'm going to show you. And I'm very happy because essentially what we do to make this semi-classical theory is to mix three results, well-known results, that people are here in the audience that make these results. One is for a quench. You know, a quench, first, I divided the talk in two parts. Essentially, the second part is small, but essentially, in the first part, I'm going to talk about a quench process. Essentially, the process is very fast, a quench. When the process is a quench, I'm going to show you that there is a relation between probability of work and the logarithmic echo. Okay? And we learn about the logarithmic echo. In fact, one of the fathers is Rodolfo, that is here. Okay? Then I will use the dephasing representation. The dephasing representation was developed by Giri and Eric Heller, and I will use that. And the quantum ergodic conjecture or the Berry conjecture is about the eigenfunction of chaotic system. I will put this together and I will make a semi-classical theory, very simple semi-classical theory of the probability of work. Okay? I said that a quench is essentially to change very fast the parameter, the piston or the magnetic field or whatever. I will work in the characteristic function. Okay, the characteristic function is the Fourier transform of the probability of work. Okay, and this was developed by Hangi, Talkener, and Lutz. That you can write the characteristic function as the trace of these 5 operators. This operator is with the Hamiltonian at the end of the process. This is the evolution operator of the process. This is the Hamiltonian at the initial of the process. This is the thermal state. And this is the evolution operator dagger. Okay? So if the process is very fast, this evolution operator is exactly 1. Okay? And in this case, the characteristic function has this form. And this form, if you look at this, it looks like what? Like the Lakshmi echo. You have a evolution with one Hamiltonian, and evolution with another Hamiltonian. Okay? But take care, because U is not time. This is the coordinate of the Fourier transform. Okay? So this was done by Silva in 2008. Okay? So if this is the Lakshmi echo for a wave function, these are the two evolutions. So if you put U equal to T divide H bar, this is the relation. The Lakshmi echo is like the probability of work, okay, for an initial thermal state, okay? And you know, many people talk here about the Lakshmi echo, that this is a measure of sensitivity to perturbation and the reversibility and all this stuff, okay? We learn about a lot of Lakshmi echo, and one of the, for me, most interesting results of the Lakshmi echo, most powerful results of the Lakshmi echo, is the dephasing representation. Okay? The dephasing representation, Giri will talk today about that. I'm showing an example. Essentially, you can write the amplitude fidelity, not the modulus. In that way, this is the amplitude fidelity, and this is the expression, the amplitude fidelity in the dephasing representation. Essentially, it's an integral in initial states, and you have the Wigner function, you have a width given by the Wigner function, and you have a phase, you move in an unperturbed orbit, and you have a phase given by the difference between the perturbed and unperturbed orbit. This is very easy to compute, okay? And this is an example. This is an old paper. We use the dephasing representation for the CAD map, okay? This is, I don't remember, the crosses. I don't remember if the crosses are the quantum or the semiclassics, okay? But look. One is the dephasing representation, and the other are the quantum. For 3 different CAD map, for 3 different Lyapunov exponent, perturbed CAD map. And you see, work extremely well. And the red curve is it's an analytical expression. You can make analytics. In fact, we wrote a paper with the analytics when we show that the Lyapunov exponent can show analytically that there is in the Lakshmi echo using the dephasing representation. Okay? Whatever. Okay. So the idea, and of course, the last ingredient is the quantum ergodic conjecture of the Berry conjecture, is that for generic classical chaotic system, the Wigner function is equidistributed in the corresponding energy shell. Okay, so you can write the Wigner function of some state in this way, with the delta function and with this for normalization. Okay, so essentially we put all these things together. We start with the dephasing. I don't want to go to the details of but the calculations are very simple. Essentially, we start with the dephasing representation. We put this is the Wigner function of the thermal state. We put here the sum on the eigenstates. Then we put the Berry conjecture of the state. This is the delta. Then we make this approximation. We need that there is the levels are not very separated each other to make this approximation. And okay, finally we obtain this expression. It's like a dephasing representation with you have a width with the thermal state. Okay, essentially. this is our approximation. This is the semiclassical expression of the characteristic function, okay, using these three elements, okay? Okay, so as I said, now I have my theory, my semiclassical expression, and I want to see if my expression describes the quantum and what happened in the semiclassical limit. In the semiclassical limit, it's very simple to, when h bar goes to 0, this exponential you can approach in this way. You can put in this way. Then you can include two delta functions. Then I make the Fourier transform here. And I come to this. I don't want to go into the details, but this is exactly the classical probability of work. So I can show analytically that in the semiclassical limit, my probability of work go exactly to the classical. So this first part, it's perfect, okay? Works. The problem is here, okay? So I want to see if my semiclassical theory describe the quantum case. For this case, I need to take, I can do analytics. I cannot do analytics. I take a system, okay? And I take a system that I know how to manage, okay? So let's see if our semiclassical expression works. I take an old friend, the stadium billiard, okay? Because I know how to compute the eigenfunction with the Eduardo's scaling method. And the quench is essentially, I start with the stadium with a potential inside that is 0, and I turn on a potential, that is Gaussians, okay? 4 Gaussians, okay? We did with 4 Gaussian, 5 Gaussian, whatever, okay? This works nice. And what we need, first we need the quantum results, okay? For the quantum results, remember, we need the initial state that it's a thermal state. So we need the eigenvalues of the stadium billiard that we know. And we need the overlap between the state of the stadium and the state of the stadium with the Gaussians, okay? And this it's easy to do. We take a base with the scaling method. We compute 3,000 of state of the billiard. We compute the potential in this base, and we diagonalize, and no problem, okay? This is the potential. The jump is from this value to this value, I think, okay? And we use the Bergini-Saraceno scaling method, okay? Let's start with the result, the numerical results, okay? This is the black curve is a semiclassical, and the other is the quantum, okay? The quantum, this is computed for, and this is the characteristic function. In the inset, I show the characteristic function. Okay, so this is for temperature equal to 64. The mean level spacing of the stadium is 7. So for this temperature, essentially, we have 10, less than 10 levels. Okay, this is a real quantum probability of work. But anyway, we can describe the main peak, okay, the black curve, but the other 3 are not described by my semiclassical expression, okay? For this semiclassical expression, if I remember well, we use 10,000 orbits, not a lot, okay? Not so much, okay? And let's take a bigger temperature. This is for 256 to 1,000 and 4,000. Look, for 4,000, our semiclassical expression were perfect, okay? Were perfect. The the characteristic function work very nice. Also for 1000, okay, works very nice. And to do the semiclassical calculation using the dephasing representation is really very easy to do, okay? You only evolves classical orbits and not a lot, okay? Okay, so the next step is let's take this probability of work, the semiclassical, and let's see if it fulfills the Harsinski equality. The points, the open points, the open boxes are the quantum, okay? The quantum, this is the quantum, is in this line, okay? Quantum, okay? And the semiclassic, look, for high temperature, this is high temperature, were very nice. So our distribution fulfills the Harsinski equality, okay? So this is really nice. But now, of course, you say, no, but you did that for a very simple process, okay? You did that for a quench. And quench is a simple process, okay. I take okay, and I say, okay. Well, this is a calculation. This is, we did, sorry, we did analytically, but we did with numerics. This is the classical distribution, the black one, and we change H bar, and you say this goes to the classical, okay? But this we show analytically, so this plot is don't have any sense. Okay, anyway, the question now is: it is possible to generalize my semiclassical work, my probability of work, for more general process? And the answer is yes. The answer is yes, and it's very simple. Again, I take a process, I take a parameter, the parameter change whatever, slowly or whatever, not so slowly, okay? I'm going to show you, I cannot make an adiabatic transformation, but I can move from the quench, okay? This is the trick. This is the generic characteristic function for the probability of work, okay? You have the 5 operators, okay? And it's very simple. Well, for the properties of the trace, I put this evolution operator here, okay? And it's very simple to show that I can put down the evolution operator here, okay? This is very simple. It's a one line you can show, okay? So if you look this looks again as a Loschmidt-Kekko, more or less, because this is not a classical Hamiltonian, okay? So we need to imagine what is this Hamiltonian, okay? Can we say that this is some classical Hamiltonian? And the answer is yes. The answer is yes. Essentially, we define a classical Hamiltonian that is the Hamiltonian at the final parameter, at the final time, in which the coordinates are evolved by the process. Essentially, this is very simple. Suppose that you have a trajectory of the unperturbed trajectory. This process evolves each point of the trajectory, and you have this one. This is the Hamiltonian. This is the trajectory of my new classical Hamiltonian. Okay. This is a possibility. Okay. This is, we thought, we don't show, but if the Hamiltonians are quadratics, this is exact. Okay. So with this one, okay, it's straightforward to have another another semi-classical characteristic function using the dephasing representation. And now the difference is here, because you have to evolve these trajectories and then to measure the final energy. Okay? But this calculation is essentially the same that I show for a quench. The difficulty of this trajectory, what is not easy is the quantum, to compute the quantum in the case of a process, okay? But let's see if this new semi-classical expression works in the same way. Okay, so the system, again, I will take a system that I know, and I change a parameter. Tau, now it's like a velocity. I change the parameter from 0 to 1, okay? And I have and I include a potential in time, okay? The system, the potential is 4 Gaussians, and the system is, again, the first lobe, you know, the stadium billiard, and we grow 4 Gaussians slowly, okay? Not like a jump, not quickly, like in a quench, okay? So here we need to first to compute the quantum probability. To compute the quantum probability, remember, this is one of the kernels. We have to compute the evolution of eigenstates at time 0 with the eigenstate at time t and evolved by the processes, okay? This is more difficult to do that quantum mechanically, but it's not so difficult. Essentially, we start with the Schrödinger equation. We write the Schrödinger equation in a perturbed basis, in the basis of the stadium. We write, here is the new Hamiltonian, and essentially we obtain this system of equations, differential equation, that is easy to solve, but not easy, but we solve in a Runge-Kutta 4 order, okay? But of course, we have to solve this one in a base of 3,000 or something like this, or not 3,000 because it's 1,000, okay? And and we compute essentially this kernel that we need to compute the probability of work, okay? So now I'm going to show you the results, the probability of work that we compute semi-classically, and the probability of work that we compute using the quantum mechanic, the exact quantum mechanic. Okay. Okay. These are the results. This is the numerics we do with this basis. We use the state up to key equal to 100. Okay. These are the temperatures. These are the characteristic function. And look, for a big, for 1,000 temperature, our semi-classical description, with this new classical Hamiltonian that we think that was okay, worked extremely well, okay? And we compute I think that we compute the semi-classics using 10,000 orbits. It's very simple, okay? This is for 0.1 the tau. Here is for bigger, sorry, this is more adiabatic. More adiabatic works worst, okay? 5 minutes? Okay. For more adiabatic work worst, and this is faster, work okay, okay? And again, we take this this probability of work and we compute the Harsinski equality, and again, for high temperature, our expression work describe the Harsinski equality. Okay? So, and I didn't want to show because it's very simple, it's the same. We can show that in the semiclassical, we can take the semiclassical expression of the probability of work, take the H bar limit, and we obtain exactly the classical expression. So again, we have a very nice expression for the semiclassical expression for the probability of work. So after that, we say, okay, this is working very nice, so let's go to the other limit. Okay? The other limit is integrable systems. Okay? My point was, it is possible that our semiclassical description work also in the integrable or mixed limit, because there are works of Giri using the Dephasing representation that works nice in the integral or mixed regime. Okay, so I take a system that is very nice because people solve analytically the probability of work. You have the expression analytically, it's very simple. This is this work of Sebastian Defner and Eric Lutz is for the quantum harmonic oscillator. Okay? Essentially, this is a system, this is an harmonic oscillator in when you change the frequency linearly. Okay? It's, and you have everything analytically, quantum. You don't have to make any numerics. I talked yesterday when everybody was taking caipirinhas, I talked with Giri during the dinner, and he said that this is the worst case, okay, for the Dephasing representation. And this is the result. This is semiclassics, and this is quantum, okay? The semiclassic work extremely well for the decay. Look, this a little oscillation can describe for semiclassics. But then the quantum has revivals, and this was impossible. Okay, I try many ways to see how to solve this problem. I couldn't. Maybe Giri know how to do it. But for the first part that I think that is important, because we have to transform Fourier this to obtain the probability of work, I think maybe the description is okay. Okay? Okay. So final remarks. Essentially, we have a semiclassical expression for the probability of work that works very nice in the chaotic case, maybe can work in the integrable case. For very, I show in a very simple system, the next step is to see, to do something like this for the many body using the Juan Diego and Klaus expressions, okay, but this is the next step that I don't know how to do it. Okay, so these are my two collaborators. Nacho García Mata is from Mar del Plata, and Augusto is from Buenos Aires. He's a colleague in the university. And these are the two papers that this is for a quench, the first one, and this is for a process. Okay? And thank you. And after this conference, I changed the word. After this conference and for this wonderful government that you have in Brazil, I changed this. Okay, thank you very much. Well, my father had to